Hello everyone, welcome back. In the last lecture, we used Nash equilibrium to analyze the market equilibrium of oligopoly markets. In fact, Nash equilibrium is widely used in game theory. In this lecture, we will introduce some basic knowledge of game theory. Learning the theoretical tool of game theory could help us understand the strategic interaction between oligopolistic firms. More generally, game theory helps us understand the strategic interaction between two or more players. Game theory has been successfully applied in many subfields of economics and in other fields such as evolutionary biology and political science. First, we should define what a game is. Game is an abstract model that describes a strategic situation. Any game must contain three elements: player, strategy, and payoff. Every decision maker in the game is called a player. The player can be an individual, a firm, or a country. Strategy refers to the actions of the players in each stage of the game. A strategy may only contain a simple action, such as whether you are speeding while driving, or it may be a contingent action plan, such as speeding only within 10 minutes after passing the speed testing zone. We usually use capital SI to represent the strategy set of player I, and small si to represent a specific strategy. Small si belongs to capital SI. Payoff refers to the return of each player, which is usually measured by the utility level obtained by the player. The simplest version is monetary payoff, such as corporate profits, but in a more general case, payoff can also be non-monetary ones, such as prestige, emotion, risk preference, etc. We use UI function to describe the payoff function of player I, where SI is the strategy chosen by player I, and S minus I is the combination of strategies chosen by all other players. In this lecture, we only discuss game between two players, which is the simplest game. First, let's look at an example of a two-players game. Suppose there are two players, player A and player B. Player A has two strategies to choose from, up and down. Player B also has two strategies to choose from, left and right. There are four combinations of strategy in total. We usually use a matrix like this to show a game. Usually, the strategy of player A is written on the left of the column, and the strategy of player B is written on the top of the row. The four boxes of the matrix represent the corresponding payoffs of the players. The first number in each box is player A's payoff, while the second number is player B's payoff. Expressing a game in this way is called normal form. So, what is the Nash equilibrium of this game, if there is one? Let's find out. First, let's look at the game from the perspective of player A. If player B chooses the left strategy, player A should choose strategy up, because up brings payoff of 3, which is more than the payoff there though brought by down. If player B chooses the strategy of right, then player A should choose strategy down, because down brings payoff of 2, which is higher than the payoff of 1 brought by up. Then let's look at the game from the perspective of player B. If player A chooses the up strategy, player B should choose the strategy left, because left brings payoff of 9, which is more than payoff 8 brought by choosing right.
If player A chooses the down strategy, player B should choose strategy right.
Because right brings payoff of 1, which is higher than the payoff of 0 brought by choosing left. Through this analysis, we can see that the optimal strategy of player A depends on the strategy choice of player B. Similarly, the optimal strategy of player B also depends on the strategy choice of player A. There are two Nash equilibriums in this game. We use up left to indicate that player A chooses up, player B chooses left. And the other Nash equilibrium is down right. A closer look between the two Nash equilibrium reveals that the payoff brought by up left is higher for both players compared to down right. But we are unable to tell which Nash equilibrium is more likely to appear. To further illustrate this issue, let's look at a famous two-player game, the Prisoner's Dilemma. The game of Prisoner's Dilemma is modeled as follows. The two suspects were arrested on committing a light crime. They are also on suspicion of a severe crime. The local police had little evidence to prove that they committed the severe crime, so they hoped the suspects to confess. The police put the two suspects in two separated rooms and told them, if you confess and turn on your partner, and your partner does not confess, then I guarantee that you can get a penalty reduction, only 1 year in prison, and your partner will be sentenced to 10 years. If you both confess, you will both be sentenced to 5 years in prison. The two suspects also know that if they both keep silence, they will only be sentenced to 2 years for lack of evidence. We could simplify the above description of Prisoner's Dilemma into the basic elements of game theory. There are two players in the game, player A and player B. Each player has two feasible strategies, confess or keep silence. We write the number of years of imprisonment as a likely payoff. We can use the normal form to represent the Prisoner's Dilemma game. Using the same reasoning as before, we can find that in the game of Prisoner's Dilemma, the only Nash equilibrium is confess. However, if we look at the payoff matrix in more detail, we will find that confess is not the best result for the two suspects. In the Nash equilibrium confess, both players face a 5-year sentence. If both players keep silence, they would only serve a 2-year sentence. Obviously, silence is a better choice. This contradiction reveals a core concept of uncooperative game. That is, if the player only cares about his own payoff and do not cooperate their actions, the Nash equilibrium result may not be optimal for any player. In the Bertrand model we learned in the last lecture, the only Nash equilibrium is both firms setting price equal to their marginal cost. This is a typical example of the Prisoner's Dilemma. If the two firms could collude to negotiate a price higher than the marginal cost, both firms will earn higher profits. But collusive pricing is not a Nash equilibrium because both firms have incentive to deviate from collusive price. In fact, we could find many examples of the Prisoner's Dilemma in life, such as price wars among producers, arms race and trade wars between countries, and so on. In the games we discussed so far, the players all make strategic decisions at the same time. These games are called simultaneous games. In some games, the players may take actions in a sequence. These games are called sequential games. Players taking action later could observe the strategic choice of the players taking action first. The Stackelberg model we studied in the previous lecture is a sequential game, where producers choose output level sequentially. Sequential games are generally analyzed in an extended form, using a game tray to represent the sequence of actions. Actions start from above, and each lot of the tray represents the decision point of the corresponding player. The payoffs of each player are displayed at the end of the tray. Let's go back to our example of simultaneous game. If player A makes decision first, choosing up or down, then player B makes a decision choosing left or right. Then this game can be expressed by this tray. In this sequential game, if player A chooses up, player B will choose left, because the payoff of 9 brought by left is larger than the payoff of 8 brought by right. If player chooses down, then player B will choose right, because the payoff of 1 brought by right is larger than the payoff of 0 brought by left. Thus, this sequential game still has two Nash equilibriums as the simultaneous game, upper left and down right. However, in this sequential game, upper left is more likely to appear and down right. This is because player A knows how player B will respond to his choice. So when player A makes decision first, he will only compare payoffs between the red and blue route.
He is more likely to choose up because the payoff of 3 for player A on the red route is higher than the payoff of 2 on the blue route.
The formal name for Nash equilibrium like upper left is called subgame perfect Nash equilibrium. We will not discuss this concept further in this course. In all the games we discussed so far, the strategies that players could choose are some certain actions. Such strategies are called pure strategies. But the player's strategy can actually be more complicated. That is, a mixed strategy, in which players choosing randomly among several feasible actions. For example, in our first example, player A can decide whether to choose up or down by tossing a coin.
This mixed strategy is to choose up with 50% probability and to choose down with 50% probability.
At a first glance, you may be surprised by the mixed strategy involving probability. But mixed strategy is in fact very common in life. To give you some ideas of mixed strategy, take the exam of this course for example. The contents of the exam should be within the materials of this course. But which parts will be examined is not certain. If we randomly choose the test content, this is a mixed strategy. And the best you can do is to review all materials. Mixed strategy also often appear in sports like soccer. For example, if a soccer player tries to shoot, he may shoot from the left with a certain probability, shoot from the right from a certain probability, and shoot straight with a certain probability. The goalkeeper needs to make judgment about those probabilities. Mixed strategies are a very important concept. One reason is that in some games, there is no pure strategy Nash equilibrium. For such games, we can use mixed strategy to predict the equilibrium outcome of the game. For example, back to our first example of simultaneous game. If we slightly modify the payoff parameters, you will find that this game has no pure strategy Nash equilibrium. But if we consider a mixed strategy, we are able to find a Nash equilibrium. One important feature of mixed strategy is that all the probabilities on different actions must add up to 1. Suppose player A choose up with probability of row U and choose down with the probability of 1 minus row U. And suppose player B choose left with the probability of row L and choose right with the probability of 1 minus row L. Then we can calculate the values of row U and row L and find the mixed strategy Nash equilibrium of this game. To summarize, for a game with finite number of players, each player with a finite number of pure strategies, there is at least one Nash equilibrium. Even if the game has no pure strategy Nash equilibrium, it must have at least one mixed strategy Nash equilibrium. This course will not discuss the calculation of mixed strategies. If you are interested, you could verify the mixed strategy equilibrium in our example involves row U equal to 2/3 and row L equal to 1/4. Alright, today we introduced some basic knowledge of game theory. This is just a very basic introduction, which we hope could help your understanding of firm behavior in the oligopoly market. Interested students are encouraged to take courses in game theory for further study. Well, this is the end of our course, Intermediate Microeconomics. Thank you for studying this course along with us.